Alright, so in this video we're actually going to be chatting about one of my favorite properties kind of in this really weird, bizarre study of these integers and in particular prime numbers. So in this case we're going to be looking at this question of looking for some really big gaps between prime numbers. So in this case we're going to be looking at this really general fact, and I'm going to do a bunch of little examples to slowly motivate this idea of how could we actually show this thing to be true, as well as kind of seeing what's actually going on in this situation, and then chat a little bit about the kind of absurdity of this actual result. So in this case, what we're doing is we're going to be given some random positive integer. In this case, I'm going to call this thing n. What I'm claiming is that there's going to be n consecutive composite integers. So in this case, if I was given the number 2, so in this case, n is going to be 2, what I'm looking for is I'm looking for two numbers that are going to be consecutive, and they're going to have this property that they're going to be not prime, or composite in this case. So what I've done over here is I've actually printed off this kind of giant list of numbers from 1 up to 50, and I've identified if they're going to be prime or not. So in this case, what I'm looking for is I'm looking for two numbers that are going to be right next to each other that both have this property that they're going to fail at being prime. So in this case, what I'm looking for is I'm looking for two falses that occur right after each other. So in this case, if you look at this, you see a false, one false, one false. Oh, there's one false here, followed by another false right happening at this situation of 9. So in this case, I know that the numbers 8 and 9, they are consecutive because they're right after each other, and they both have this property that they're going to be not prime. In this case, I know that 2 divides 8, and I know that 3 divides 9, so I know these things are going to be not prime. So I could ratchet this thing up one step higher. So in this case, if I'm looking for 3 consecutive numbers, none of which have this nice property of being prime, you can actually see that we were really close to finding that right away in this beginning, because I know that 8 is composite, so is 9, and now I can see that 10 is going to be as well, because 10 is actually another even number, so I'm going to have another factor of 2 in this case. So in this situation, I know that there are going to be 3 numbers that are going to be next to each other, none of which being prime, if I look at the numbers 8, 9, and 10. What's interesting is if I start to kind of ratchet this up a little bit. So in this case, if I look at n being 4, well, I no longer can use this information about 8, 9, and 10, because what's going to happen is that I'm going to jump up to an 11, and I know that 11 is actually prime, so I'm kind of maxed out at that situation. I have 3 consecutive numbers there, but I don't actually have 4. So I got to go down this tree a little bit farther. So I'm looking for a group of 4 falses. So you can see that there's a couple different groups of 3, but then there's a group of 4 that's actually going to start right here at 24. So in this case, a run of 4 numbers is going to be a 24, a 25, a 26, and a 27. You can actually see in this situation, it's kind of nice that once I have this kind of run of 4, it's pretty easy to find the run of 5, because I'm just going to pick up that next even number afterwards. So in this case, I have my run of 24, 25, 26, 27, and 28. So all is great. I mean, that seems like an easy enough thing to do. If I'm looking for a group of 2 numbers that have this property of being not prime, that's pretty easy. If I'm looking for a group of 3, it's not so bad, and being 4 and 5 took a little bit farther, but it still wasn't terrible to actually kind of dive through this thing. What's problematic though is if I want to think about generalizing this thing for n's being really large. If I wanted to find a run of 100 numbers that have this property that none of them are going to be prime, what I'd have to do is I'd have to create this gigantic list, and I don't really know how high I'd have to go, and I have to kind of run this little search algorithm to look for, in this case, 100 straight falses in this case. And that's somewhat taxing and a little bit annoying actually to work with. So what I'm hoping to do is see some type of structure actually underlying this, so I know a little bit about kind of where these things should be. And what I'm going to do in this case is I'm going to start to really dive into this idea of what does it mean to be not prime. And this idea of how can I build up some of these nice factors that I know exactly what these objects are going to be divisible by. So in this case, what we're going to be doing is we're actually going to be trying to think of other groups of numbers other than these ones that were given here that are going to kind of start up this process of really starting to see a bunch of these little factors occurring. What we're going to be relying upon is this notion of this factorial. So in this case, if you remember what 4 factorial is, 4 factorial is simply just 1 times 2 times 3 times 4. And you can see that this thing is going to be built up in a really nice way that has this special property that there's all kinds of factors floating around in these things. I know that 4 factorial is divisible by 2. I know that it's also going to be divisible by 3, as well as being divisible by 4. So that's what I'm going to actually use to try to find another run of things that are going to be kind of not prime in this case. So what I want to do in this case is I want to look at this number 4 factorial, and I want to think about adding something to it that's going to keep this notion of having some really nice divisor. So in this case, if I look at 4 factorial, if I were to add, let's say, a 2 to it, what's going to happen is I'm going to get 1 times 2 times 3 times 4 plus a 2. So in this case, the thing on the left and the thing on the right both happen to have a 2 in it. That is, I could actually factor a 2 out of this thing, giving me a 1 times a 3 times a 4 plus a 1. And I know immediately that that thing is still going to be divisible by 2 because I have that little 2 out in front. So in this case, what I have is I have the number 4 factorial plus a 2, which if I actually compute what this thing is going to be a 26, is going to be a number that is not prime. And that's great, whatever, I have a number that's now not prime. What's nice about this, though, is that I can churn this process one more step. I could look at this idea of 4 factorial plus a 3. Doing the exact same process that I did up above, I know that this special new number is going to be divisible by 3 because I have a 3 here and a 3 there. And in this case, if I actually compute this thing, it's the number 27. So in this case, I have a nice way to see 2 consecutive numbers, and both of those things are going to be not prime, because this thing's divisible by 2 and this thing's actually divisible by 3. If I move that one more kind of up, I'm going to have this idea of adding 4 to it, which is going to be a 1 times a 2 times a 3 times a 4 plus a 4 in this case. You know that this funky number is going to be divisible by 4 because both of those things have a 4 in it, and we know that this number is simply just going to be a 28. So I actually have another run of 3 numbers, in this case the numbers 26, 27, and 28, that have this special property that they are going to be not prime. We actually have a little bit more going on in this case. We know that 26 is divisible by 2, we know that 27 is divisible by 3, and we know that 28 is divisible by 4. So it's kind of leading us into this idea of how can we construct these really crazy objects. So if I wanted to, I could actually push this idea a little bit farther. So I just looked at this example right here, this idea of if n is going to be 3, I can look at this idea of taking 4 factorial and adding 2 to it, adding 3 to it, or adding 4 to it. So in this case, if I wanted to look for a run of 4 numbers that are going to have this property that none of these things are going to be prime, what I could do is I could look at 5 factorial, and I could add 2 to it to give me 122. I could add 3 to it to give me 123. I could add 4 to it, which is going to give me 124, or I could add 5 to it, which is going to give me 125. So in this case, I know that this thing is going to be divisible by 2, this thing is divisible by 3, this is divisible by 4, and that's divisible by 5. So what's nice about that is, again, they're a little bit larger than the numbers that I was initially working with, but it's going to give me this kind of slightly more insight into this idea of how can I construct 4 numbers that are going to have this property of being not prime. If you wanted to, you could ratchet this up just a little bit farther and see this idea of looking at, let's say, 6 factorial plus 2 plus 3 plus 4 plus 5. In this case, what's going to happen is that I'm going to get these nice things. All of these things are going to be not prime, and in this case, they're going to be composite. So if you wanted to really kind of dive into the nitty-gritty on how that situation works, I do have a little bit of extra information of showing this idea of if you take n to be 5, what's going to happen is that I'm going to look at 6 factorial. So I'm going to add 1 more to this thing. So I'm going to look at 6 factorial along the way, and I'm going to either add a 2, a 3, a 4, a 5, and a 6. So in this case, you can see that those 5 numbers are all going to be consecutive because they're all differing just by 1 in this case, which in this case is going to give me the numbers 722, 723, 724, 725, and 726. And we know these things are all going to be composite. Because of the way this factorial is built up, I know that that thing is going to have all of the factors I'd ever want to up to 6. I know that there's a 1, 2, 3, 4, 5, and 6. So adding a 2 to that thing can simply just be factored out, which is going to say that this object is divisible by 2. Likewise, if I add a 3 to it, it's going to be divisible by 4 or by 3. And if I add a 4 to it, it's going to be divisible by 4. Adding a 5 is going to make it divisible by 6. And adding a 6 is going to make it divisible by 6. So in this case, you can see that I'm going to have another run of 5 consecutive numbers that have this really special property of being not prime. So before I go ahead and actually show you the kind of crazy actual result for this thing, I just want to chat about kind of, like I mentioned earlier, this somewhat absurdity or kind of craziness about what this statement's actually saying. So this statement's going to say that if you give me any value of n, so in this case, I do really want to stress this idea that n can be anything. if you give me any random number, I'm going to say that there are going to be n consecutive numbers that all fail this process of being prime, which is kind of a funky thing to think about. So if you start off relatively small, let's say if I give you n being 9, what I'm saying that there's going to be a run of 9 consecutive integers where none of them are prime. In this case, we actually have a run of these things not so high up, actually. If you go from 140 all the way up to 148, you know that those numbers are all going to be not prime, which is kind of a strange thing. There's this kind of, you feel like there should be a prime along the way somewhere, but there's not. And that's actually one of the really kind of funky things about prime numbers is that below 100, they're actually grouped pretty closely together. There's a whole bunch of prime numbers less than 100, and they're not that far apart. You know, there's not really huge, crazy runs below 100. I'm going to have these kind of nice little groupings. But as these numbers become larger, I have this potential of having this really long string where I don't have any prime numbers. So in this case, I could have a run of 9 straight numbers, and none of them are going to be prime. What's worse is that, again, I'm having this idea that n could be anything. So if n is going to be, let's say, 100, what I'm claiming is that somewhere in the world of the numbers, there's going to be a run of 100 consecutive numbers where none of them are prime, which is, again, a really weird thing to think about. You're thinking these, I see a whole bunch of primes, but now all of a sudden you have that little algorithm looking, and you might have to run this thing 100 times before you find the next prime number. Likewise, if n was, let's say, 10,000, so now we're ratcheting this up pretty large. What this is going to say is that there's going to be a run of 10,000 numbers, and none of them are prime. So in this case, you find some prime number, you're going to have to run this thing 10,000, possibly more times before you find the next prime number. What's even worse is that n could be, let's say, 1,000,000. What this is saying is that in this kind of collection of numbers, there's going to be a gap where you're going to have some prime number, and then there's going to be 1,000,000 numbers that are going to occur before you find your next prime, which is, I don't know, I think absurd to actually think about. There's this, like, I don't know, if that one even hurts my brain in a sense of being like, oh man, I know a little bit about what prime numbers are all about, but now all of a sudden I'm going to find a prime number. My little algorithm's going to look for 1,000,000 straight numbers in this case, and it's not going to find another prime number. So in this case, we like to think about these primes as being pretty close together, at least down low. But in a sense, we're kind of lucky. Maybe, you know, if we didn't have this notion of prime numbers until the number of million, we'd have these kind of really difficult concepts about what primes are all about. What's even worse, though, is that n could be even as big as you could ever imagine it to be. So in this case, if n is the size of the number of atoms in our entire universe, and I have no idea what that number actually is, but it's some number, and it's massive. It's ridiculously massive. What this result's going to say is that there is going to be that number of consecutive numbers that have this special property that none of those things are going to be prime, which is absolutely absurd to think about in this case. Is that I have this notion on one side that I know that there's going to be an infinite number of prime numbers, but on the other side, I could have, you know, the size of the universe before that next prime number actually occurs. So in this case, it's this idea that I get up to a certain stage, and then I got to run an algorithm for a long time. In this case, the number of atoms in the entire universe amount of time before I possibly find that next prime number after it. So like I said, it is one of the craziest, nicest results ever, but it's also one of the makes your brain hurt kind of results as well. It's totally believable, at least for these small numbers. It gets really bad as you go down this tree. This idea of having massive numbers is going to make this thing crazy and horrible. So if you're interested in actually seeing how you would show something like this, actually the result is exactly that kind of example that we saw when n was going to be 3. So in this case, what you're going to do is you're going to give me this number n. What I'm going to compute is I'm going to compute that number plus 1 factorial. So when I was looking at trying to find a run of 3 numbers, what I did is I took that 3, I added 1 more to give me 4, and then I computed the factorial of that thing. The idea is that 4 factorial, so in this case, 4 factorial looks like a 1 times a 2 times a 3 times a 4. Well, the problem is that adding 1 to this thing isn't going to help me see factors. So I'm going to add a 2, I'm going to add a 3, and I'm going to add a 4, which is why I had to go 1 larger. So if I'm given 3, if I want to find 3 consecutive numbers, I have to start this game off at n being 4, or at 4 in this case. So what's going to happen is that if you give me some value n, I'm going to look at n plus 1 factorial, And then in this case, I'm just going to add some extra number. In this case, that number that I'm going to add is going to either be a 2, a 3, a 4, a 5, all the way up until I get to that number that I started with. And that's exactly it. That's all you got to do in this case, is that if you look at this funky expression, what's going to happen is that I know that there's going to be a k somewhere in that factorial, and I know that I'm going to be adding a k to this thing. It's the exact same as if I look at 4 factorial plus a 2. I know that there's a 2 over here, there's a 2 over there, and I can actually factor that 2 out, giving me some expression like this, which is going to say that that thing is divisible by 2, or in general, it's going to be divisible by k. So what's happening here is that I'm factoring this little k out, which is exactly what's occurring there. So now it's k multiplied by some stuff, and I know that that thing is going to be divisible by k. So in this case, what's going to happen is that that is going to create this chain of a whole bunch of numbers that are all going to be consecutive, that are all going to share this property that they're going to be not prime. Because the first one's going to be divisible by 2, the next one's going to be divisible by 3, and then 4, and then 5, all the way up until n plus 1 in this case. So that's going to give me my run of n consecutive numbers, none of which are going to be prime. So in this case, it is a really cute kind of little application or extension of this idea of factorials. It is most certainly a trick in this situation of actually coming up with something like this is very challenging, but once you have it, it's actually a pretty nice thing to look at. So like I mentioned, if you at least understand kind of how this one works, that's all I really care about, as well as kind of the overall absurdity of how these prime numbers function, is really what I wanted to instill in this idea, is that these prime numbers have fantastic properties, but they also have some extremely bizarre properties that make absolutely no sense at all. And this is going to be one of those properties. But as we've kind of alluded to a few times, the absurdity of these prime numbers is exactly what makes them so alluring in this world of cryptology and crypto systems and things like that. If we had some knowledge of how these things behaved really well, if they behaved really well, they would no longer be useful in this world of kind of using them to make things more secure and stuff like that.